Welcome to today's class, Deadlock Avoidance. In the Deadlock Avoidance, I will discuss about the what is safe state, resource allocation graph and the banker's algorithm. In the banker's algorithm, safety algorithm, resource request algorithm. The first one is the two approaches are used for the deadlock avoidance. In the first approach, the do not start a process if the demand might leads to a deadlock. And in the coming to that second approach, the do not grant a resource request to a process if that allocation might lead to a deadlock. So here the resource allocation state, mainly the deadlock avoidance algorithms examines the resource allocation state. The resource allocation state defines this resource allocation state defines number of available resources and allocated resources and the maximum demand of a process. So that means in the resource allocation state, in that resource allocation graph, we will concentrate on the available resources and the allocated resources and the maximum demand of a process. Now the first one is, what is safe state? The safe state is a state in which there is at least one order in which the processes finish the execution without leading to a deadlock. So here let us consider the process P1 to the process Pn is a safe sequence. When that sequence is called the safe sequence means if one process finish the execution, for finishing of the execution, if that process request for the any resources, that request can be satisfied by that number of available resources. So here that type of sequences are called that safe sequences. So here the unsafe sequence is not called that exactly the deadlock state. The deadlock state is called that unsafe state. So the all unsafe states are not the deadlock states. Sometimes the unsafe states may lead to that deadlock states. So let us consider one example. In this example, consider the three processes, the process P1, process P2 and process P3 and one resource with R1, the resource R1 having the 12 instances. So in these three processes, the process P1 and process P2 and process P3, the process P1 requires the 10 resources of R1 and process P2 requires 4 resources of R1 and the process P3 requires 9 resources of R1. So here the operating system allocates the resources to these processes as this following. Now the process P1 holding holding 5 resources of R1 and the process P2 holding the 2 resources of R1 and process P3 holding the 2 resources of R1. So here clearly understood. So here the 3 processes are there. In these 3 processes, for the finishing of that execution, the P1 requires the 10 resources and the P2 requires the 4 resources, P3 requires 9 resources. But the operating system assigns the 5 resources to P1, 2 resources to P2 and 2 resources to P3. Now the total the R1 having that only 12 instances only. So in this regard, what I said already, processes. How many processes are there? the three processes, process P1, process P2 and process P3, and the need of the maximum demand of each process for the finishing the execution, the process P1 10, the process P2 4 and for the process P3 9. But the current allocation is 5 to P1 and 2 resources to P2 and 2 resources to P3. Now the available resources are the 12, already 9 resources are allotted to P1, P2, P3. Now that available resources are 3 resources. Now to say that if the safe sequence in these 3 processes, first we start with the process P1. Before starting that process P1, we should know that what is the need of each process. For the process P1, for the finish of the execution, we just need to know that the need of the process P1. How to get the need of the process P1 means the allocation minus maximum demand of each process. Now that the need of the process P1 is 5, the need of the process P2 is 2 resources and the need of the process P3 is 7 resources. Okay. Now first we start with the process P1. But how many available resources are there? Now the available resources are 3, but it requires the 5 resources to finish that execution. So now we'll move into that process P2. For this process P2, it need only the 2 resources to finish the execution. But here available resources are 3. So now it is enough to finish the execution of process P2. Now the process P2 finish the execution. Now that available resources are, after execution of this, after finishing of this process P2 execution, the process P2 returns to the system. These resources will be added to the available resources. Now that available resources are 5. Now we go to the process P3. Process P2 finish the execution. Now we will move into the process P3. The process P3 needs the 7 resources for the execution, but the now available resources are only 5. So it will not sufficient to finish the execution. So that is the reason we will move into the process P1. So for the process P1, the need is 5 resources. So now available resources are also 5. So now process P1 finish the execution and now the available resources are 10. What is the leftover process now? That is the process P3. Now for the process P3 requires 7 resources. So here in this 10 resources, 7 resources are available. So it uses the remaining 7 resources and finish the execution and it returns to the system and those available resources will add to the available resources. So now the total how many instances are there? The total 12 instances we have already considered. So now we can say that this system is in a safe state and this is the safe sequence of these given processes. Okay. So this is all about that what is safe state. Now coming to that resource allocation graph. Okay. In this resource allocation graph, you already know about the what is request edge and what is assignment edge. The request edge is from the process to resource. That means the process P1 is request for resource Rj. The coming to that assignment edge, that assignment edge from the resource to process. This means the process P1 holds the resource Rj. So now, in addition to these two edges, we use the climb edge in resource allocation graph. Okay, the third edge is new edge, that is the climb edge. Now we are using this climb edge in resource allocation graph. This is resource R1, this is resource R2, and we are using the two processes, process P1 and process P2. Now this process P1 holding that resource R1 and that process P2 is request for that resource R1, and these are the two climb edges. So actually the climb edges are represented with the dashed lines in the resource allocation graph. It resembles like that request edge only, but we are representing with the dashed lines. Suppose if you see that a climb edge process Pi to resource Rj means the process Pi request for the one resource at some time in the future. So let us consider if process Pi request for the resource Rj in the future, the first it converts into that request edge. So in this resource allocation graph, this dashed lines represents the climb edge. Okay, so in this climb edge, so for this climb edge, first we convert into the request edge. So after that, once this resource is assigned to that particular process, that is converted into the assignment edge. The once that process finish that execution, again it is reconverted into the climb edge. Okay, this is about the usage of climb edge in that resource allocation graph. So in this we can use that cycle detection algorithm. So if there is any cycle form in this resource allocation graph, we can say that the system is not in a safe state. If there is no cycle exist in this resource allocation graph, okay, so that system is in the safe state. If you consider the same example in this resource allocation graph, suppose if the process P1 is request for the resource R2, but we cannot allocate this resource R2 this process P2. Why? Because here the process P1 is requested for the resource R2 and this process P1 holds that resource R1. If we assign this resource R2 to process P2, so it will not finish this execution. It will be in the waiting state only. So until and unless it finish the execution, it will not release that resource R1 to the P2. So then it will lead to the deadlock state. This is all about the resource allocation graph.